Hi everyone, my name is Clare Cook and I'm a fourth year PhD student in the Computational Optics Lab at Duke. In this video, I'm going to share a little bit about my work developing a ultra high-speed Fourier light field imaging system for measuring exoskeleton deformations in snapping trapjaw ants. And this work was done in collaboration with the Patek Lab, also at Duke. I'll start by introducing you to the trapjaw ant. Like most ants, trapjaw ants live in colonies and spend much of their time hunting and maintaining their nests. But unlike other ants, the trapjaw ant has been named a contender for the fastest animal on Earth. They can't outsprint a cheetah, but they can snap their mandibles, which are these specialized appendages on the ant's jaw, with incredible speed. These ants can accelerate their mandibles faster than a bullet to hit speeds up to 200 miles per hour in a fraction of a millisecond. The power to weight ratio necessary for such a small animal to produce these snaps is comparable to that of a rocket engine. And incredibly, trapjaw ants can repeatedly produce this amount of speed without damaging themselves. As we can see in this video from Dr. Adrian Smith, they are regularly using these mandible strikes for fighting, hunting, and jumping. And biologists are very interested in understanding the mechanism behind these jaw strikes, as it could have important implications for efficient energy storage, non-destructive energy focusing, and the design of micro-robotics. Biologists working on this problem have previously found that the trapjaw ant mandible strike is enabled by latch-mediated spring actuation, or LAMSA. In LAMSA mechanisms, an actuating muscle is used to slowly load a spring-like mechanism in the organism's body. The spring is held in place by a latch. When the latch releases, the spring recoils, rapidly releasing all the stored energy. In the case of the trapjaw ant, the spring is actually the ant's exoskeleton, which deforms during this loading and release process. But currently, we still don't really understand how the LAMSA spring works in trapjaw ants. To understand how the exoskeleton stores and releases this much power, it is crucial to observe and quantify how the ant's head warps and deforms while it's striking in 3 dimensions. Unfortunately, there are not any existing imaging systems that can record specimens of this size in 3D with the needed precision and speed. Biologists can capture conventional 2D videos of the striking ants and observe these regions where deformations are taking place. They can also perform micro-CT scans on dead or anesthetized ants to see their 3D anatomy, and they can try to puzzle together how the 3D structure fits in to the 2D videos. But they have no way of directly observing what's happening during the mandible strike in 3D. So to solve this problem, my lab has teamed up with the Evolutionary Biology Lab under Sheila Patek to create a new imaging system that can allow us to analyze the trapjaw ant strike in 3D for the first time. So this is our solution, the ultra high-speed Fourier light field mesoscope. This system uses Fourier light field imaging to project 3 multi-perspective images of a single trapjaw ant onto an ultra high-speed camera. We then pass these images through our image processing pipeline to extract the 3D deformation in the ant's exoskeleton. Using our approach, we can film strikes at 100,000 frames per second and visualize micron-level deformations occurring over the full millimeter scale field of view of the ant's head. To explain our hardware design, I'll first discuss our imaging sensor, the far-sighted Photron E980S camera. This camera can stream at up to 2 million frames per second, or 270,000 frames per second at its full resolution. Importantly, the camera has large internal storage, which allows us to capture about 15 seconds of film when recording at 100 kilohertz. This is critical when you're working with live animals who may not strike on demand. And this camera has already allowed the Patek Lab to capture high-quality 2D video of striking trapjaw ants. Then we can use Fourier light field imaging to form multi-perspective images of our sample onto the Photron sensor. In their most basic form, Fourier light field imaging systems consist of an array of small lenses placed in a 4F configuration behind a large primary lens. Each of these lenses forms an image of the full field of view onto the sensor. When objects in the field of view move axially, those movements are encoded as lateral shifts in the image plane, and the magnitude of those shifts corresponds to the distance between the array lens and the optical axis. So in this diagram, when the points shift, their projection in the center image does not move, but their projection in the lower image shifts up. As a result, we can use these shifts to measure the 3D movement of points. Here's our physical setup. We are using 3 individual array lenses which sit together in a 3D printed box. For our primary lens, we are actually using a macro-scale machine vision lens, and we illuminate our sample with strip illumination placed in front of the primary lens. This is what our full imaging setup looks like, and we mount the ant right here for filming. This is a raw video from the system. We have 1, 2, 3 views of the same ant. This is dental wax that we use to mount the ant. Here's the mandible, which we'll see strike in a moment, and this is the ant's cheek, which is the region of its head that we're wanting to study. In these videos, we've actually finally spray painted the ant with white paint to create features that we can track. So I'll play the video, and we will see the ant strike. And even here we can start to see how the exoskeleton is deforming a little bit. But next we need to extract the quantitative 3D motion from the video. In traditional depth from stereo, depth information is computed by matching features between images. However, with the large pixel size of the photron sensor, many of the features only cover a couple pixels and they can be challenging to match precisely. And more importantly, even if we could match features with single pixel precision, the axial resolution would only be about 74 microns, and we really want closer to 5 micron precision to resolve these deformations. So instead, we are using optical flow, which is a technique that uses changing pixel intensity to compute sub-pixel movements. With this approach, we manually match features between the views in a single video. Then we perform optical flow tracking in each view separately. This allows us to get far higher precision for 3D movement as opposed to absolute position. Here's how that actually looks. This is the first frame of a strike video. We're going to track this point in the 3 views. So that gives us 6 total movement vectors for this point. It's X and Y movement in all 3 views. And I'll point out the units on the axis. The point barely moved a full pixel in any one direction. From there, we can use a calibrated model of our system to go from the 2-dimensional optical flow to its 3-dimensional movement in space through all 80 frames of the video. If we repeat this process for many points on the ant's head, we can take the average of that to find the global movement of the ant's head, and anything remaining is the 3-dimensional exoskeleton deformation that we're wanting to measure. This is an example video from the system. Here's a single view of the ant's head. This is its mandible and its cheek. We're going to watch the movement of all these points. The arrows are going to indicate lateral movement, and the color will indicate axial movement. So I'll let that play. So we see the head compressing in and up, and the largest axial deformation right here in the center. Here's another presentation of the data where we can trace out the precise axial displacement for each point. And we can again see how this center region of the ant's head experiences the largest axial displacement. So we've now used our system to record videos of 329 strikes from 29 different ants. By projecting all of the tracked points onto the same coordinate system, we can see how consistent the pattern of deformation is between strikes. I'll let this video play. We can see how the ant's head consistently elongates vertically, compresses horizontally, and we once again see this large region of axial displacement right in the center of the ant's head. So we're now using this data set to finally understand the mechanism and physics behind the power storage and release during these mandible strikes. Thanks for listening.